Thank you for introducing me. I'm Yuki Kyogoku. I'm a doctoral candidate at the Leipzig University, and I thank you, Amano-san, for inviting me to this workshop as a speaker again. Today, I'm going to talk about assessing semantic similarity in Sanskrit using word embeddings with a weighting factor. I have to tell you in advance, if you didn't hear my presentation last year, it will be sometimes difficult to follow because I try to avoid the same explanations that I did last year because of the time limitations. So my apologies. So I start my presentation. Here is the outline of today's presentation. First, I'm going to talk about research objective and digital corpus. And next, I'm going to show you the main body of this presentation, method and evaluation. And lastly, I show you the results and I summarize them. So the research objective is to quantitatively evaluate 4 models proposed for the task of comparing the similarity of chapters in Maitra Yani Samhita, Tatriya Samhita, and Kataka Samhita. The performance of the models is compared with a human evaluation, which is chiefly based on parallel passages. And lastly, I examine the effects of weighting factor and vector type on presentation. As for the digital corpus, just as last year, I used the same Sanskrit corpus of Dr. Helvig, which you can find in his GitHub page. The information about the training corpus and target text are as you see here. And the number of chapters is counted based on chapter ID in the Conlu files. So I accept the artificial divisions, even though they do not necessarily correspond to the ideal chapter division in terms of parallel passages. So that's the corpus information. Now I'm gonna show you the main body of this presentation. In this section, I propose 4 different models, which I'll compare with each other. All the models are created based on word embeddings. A word embedding is, to put it simply, a type of word representation of a word. For example, a word can be represented in this way. It's very powerful to find semantic similarity, and one could achieve the same aim by means of n-grams, topic modelings, BART, and so on. But this time, just as last year, I just focus on the word embedding because it can get a handle on semantic scheme of words, and it is there to be easy to adjust. So to create the 4 models, I employ 2 aspects. The first aspect is word vector type. So either by word to back or fast text. The other aspect is the method of creating chapter vector. So by averaging or normalized weighting of word vectors. So I first generate word vectors, either by word2vec or fast text. Second, I generate chapter vectors, either by averaging the word vectors or by weighting the word vectors. Last year, I simply averaged the word vectors created by word2vec, but this is the simplest way to create the chapter vectors. So this time, I introduce fast text and weighting vectors as new things in order to improve the model last year. Next, I'm going to explain the fast aspect, namely the difference between word2vec and fast text. Word2vec is one of the most popular word embedding models, and I used it last year to obtain word vectors. A word2vec model is trained at the word level or token level. As you see here, if the orange is the target word, apple, and N, and A are regarded as the context given the window number 2 or 5. It depends on which application you use. The training doesn't take much time. It's one of the advantages of word2vec, but 2 less frequent words are to be removed because otherwise the context would be biased. And just as last year, I fed word2vec with lemmas instead of tokens. On the other hand, fast text is trained at the level of character. That means if the target character is N in the word orange, its context is R, A, G, and E, given the unigrams. Its training takes much more time than word2vec, but fast text has a lot of advantages that word2vec doesn't have. Especially, it is effective for morphological rich languages, and the model generates word vectors even if the words do not appear in the corpus. So when I trained it, I didn't remove grammatical syntaxes and subwords or functional words that appear too frequently, because they also reflect the grammatical subtlety of a corpus. I would say fast text is much more promising for Sanskrit. So because of this, their different characteristics, I fed fast text with tokens, and I fed word2vec with lemmas. Now I'm going to talk about the second aspect of the model creation, that is how I created chapter vectors given these word vectors. I propose 2 ways. Firstly, I created them by simply averaging word vectors in this formula. Secondly, by weighting word vectors by TF-IDF, that is term frequency and inverse document frequency. In the end, I compare the chapter vectors by cosine similarity, just as last year, and to measure the semantic distance between the chapters. The averaging word vectors is exactly the same way as how I did last year. And the other way, TF-IDF is also a well-known idea. It is often used to measure the importance of words. And it is one of the simplest and most common keyword extraction methods. And this is a paper that proposes a word embedding model weighted by TF-IDF. And the paper reports that the model weighted by TF-IDF outperforms some state-of-the-art models like Dr. Beck. In the following slides, I'm going to briefly show you what the TF-IDF is. So TF-IDF consists of TF, time frequency, and IDF, inverse document frequency. Here it is TF, time frequency. First, you simply count how many times the word appears in the document. However, the same word in a larger document appears more times than in a small document. So in order to remove that bias, the simple frequency is divided by the total number of tokens of the document. Nevertheless, alone, the term frequency TF is still not enough because most of the frequent words are less significant, like articles in English, such as the and are, which do not carry much information. So here, IDF, inverse document frequency, comes into play. The formula looks a bit more complex than that of time frequency, probably because of this logarithm. But just for the sake of simplicity, you can ignore it because it just moderates the whole value. For the calculation of IDF, you first count the number of documents in which the target word appears. And N denotes the total number of documents. And since N doesn't change depending on the term T, a given word that often appears in other documents produces a lower value. On the other hand, a word that appears in only a few documents produces a higher value. So that's IDF. Finally, this TF is multiplied with this IDF. So a higher TF IDF value means that the word appears many times in the current document, but it does not often appear in other documents. And the word that too frequently appears in other documents gets a lower value of TF-IDF, even if it appears many times in a certain document. So now we are going back to the model with weighting vectors, which I propose in comparison with the model with averaging. In this model, when adding word vectors, each word vector is weighted by weighted with the corresponding TF-IDF value. So significant words are more heavily weighted. There are actually more things to talk about this model, but because of the time limitation, unfortunately, I have to skip them. So this is the summary of the models. I introduced the new two aspects, namely word vector type and the method of creating chapter vectors. Each aspect has two choices. So 2 times 2 is equal to 4. So I propose the following 4 models. Word-to-Beck and average is exactly the same model that I used last year. And the remaining 3 models proposed from the new aspects. So that's about the models. Now we are going to see how to assess the four models. So we will see which model works better. In the evaluation, I compare the chapters systematically extracted by each model with a human evaluation. So I asked Amano-san to extract similar chapters, and I regard it as a human evaluation. But the similarity can be interpreted from some aspects. In this study, I put more emphasis on vocabulary and topics, because word embeddings take more advantages of their characteristic in this respect. So I asked Amano-san to extract similar chapters from this perspective. In this slide, I show you a bit more precisely how the evaluation procedure is done. MS chapters are compared to TS and KS chapters based on vocabulary and topics as a similarity measure, especially on the fact that the chapters share parallel passages. A human evaluator, in this case Amano-san, assigns the most similar TS or KS chapters to each MS chapter. The top 3 most similar TS or KS chapters for each MS chapter are extracted by the 4 models. Here I have to note that in general, one TS or KS chapter is assigned to each single MS chapter as the most similar chapter by Amano-san. But to some MS chapters, more than 2 TS or KS chapters are assigned as the most similar chapters. On the other hand, the 4 models always exact the top 3 most similar chapters, irrelevant of how many chapters are assigned to an MS chapter by Amano-san. Now, I also have to say that the same chapter assigned to a certain MS chapter can be also assigned to other MS chapters. So now I pose a question. Are the most similar chapters extracted by the human evaluator contained in the top 3 chapters extracted by a given model? A model that extracts more similar chapters is to be regarded as a better model. So this is the basic idea of evaluation. In the following 2 slides, I'm going to show you how I counted similar chapters. In the result, there are 2 kinds of chapters. There are chapters that are correctly extracted by the model. That means the chapters that are properly classified as similar chapters by the models, just as done by the human evaluator. But on the other hand, there are also chapters that are extracted as similar by the human evaluator, but not extracted by the model. The former is called true positive. The latter is called false negative. The performance of the models is evaluated by the division of true positives by the addition of both true positives and false negatives. Here is the general formula. It's called recall. And this is the specific formula for the current case. So the number of chapters properly extracted by the model is divided by the number of all the chapters evaluated evaluated as similar chapters by the human evaluator. Recall is usually used as a pair with precision, but I don't show you precision in this case because it's just proportional to recall now. So now I'm ready to show you the result. Here is the result. As you see, what to back and average, with the same model as last year, brought the best result among the 4 models. And the second best model is what to back and TF-IDF. Third best model is fast text and average. And the worst model is fast text and TF-IDF. The result is totally opposite to my expectation. This time I introduced 2 new things, namely fast text and TF-IDF. However, both, so to say, failed to improve the model last year. In German, I would say verschlimmbessern, in Japanese, kaiyaku. But concerning TF-IDF, it is not necessarily the case. On the whole, as you saw, the simple average works better than TF-IDF weighting. However, Amano-san pointed out, for the specific pair MS 1.8 and KS6, the models with TF-IDF weighting extracted more similar chapters than the models with averaging. I have a guess at the better performance of TF-IDF in this respect. Actually, the parallel passages with MS 1.8 do not concentrate on a certain portion, but they are scattered in KS6. Moreover, the chapter size of KS is larger than that of TS. So the models with averaging treat irrelevant words in the same way, just as relevant words. On the other hand, TF-IDF, I guess, TF-IDF may be capable of capturing the characteristic vocabulary in chapters, and it emphasized the scattered keywords. That's my best guess, but it is still under investigation. To summarize, I'd like you to remember some important points in this presentation. In terms of vocabulary and topics as a measure of similarity, the simplest model, namely word to back and average, brings the best result. But in some specific cases, TF-IDF weighting may be capable of capturing some characteristic vocabulary. So perhaps, I would say, I would emphasize the perhaps, TF-IDF weighting is more effective for a larger text in which keywords are widely spread. And concerning the poor performance of fast text, it is also very surprising because it is generally said fast text is effective for morphologically rich languages. This time I use a Python library called Gensim for fast text, and I simply applied it without changing the default parameters. And I guess the poor performance of fast text can probably be improved by optimizing its parameters. If any of you knows more about the parameters of fast text which I could modify, please let me know in the QA time or later. So the last 2 points are just out of my speculation, but I'll try to examine them by testing the models from various points of view. As for fast text, it's a good starting point to evaluate its word vectors instead of chapter vectors by seeing it if it succeeds in extracting synonyms in the text like Amara Kosha. Last but not least, there are a lot of things to improve in my presentation, especially the way of variation, I think. I could have grouped some chapters as semantic unit, just as Amano-san suggested. And Amano-san is also interested in comparing chapters within MS instead of comparing MS chapters to TS and KS chapters. So comparing MS chapters to foreign chapters of TS and KS. I'm also ambitious to try such things as a further study. I think that's it. Thank you for listening.
Oh, thank you for the really interesting presentation. And do you have any question or comment? Oh, please ask, Oliver.
A very good question. Which corpus did you train your fast text model on? So which text did you
exactly the same? I trained the fast text models with exactly the same training corpus with as Waterbeck. I excluded the training chapters in the process of training. So MS, TS, KS are excluded from in the training process, and I did the very same thing in just as in the process of the training of Waterbeck. But nevertheless, I got a poor performance of fast text.
Just an idea. So basically, fast text is unsupervised. So you could basically take any Sanskrit text you can get. For instance, you could take the whole Greta repository and just put it into fast text. And in this case, I would guess you get better results than you have now. So just take whatever you get in Sanskrit and put it in and see if something changes. I don't know, but you need to restrain yourself to only lemmatized parts of the corpus. So just a side note.
Okay. There's a difference. I've just hit upon the difference between the trainings of Waterbeck and fast text. I trained, just as mentioned in the presentation, I fed Waterbeck with lemma. On the other hand, I fed fast text with tokens. This is also one of the differences between them. Maybe
at this point, I would like to ask, did you try to train fast text on the lemma as well, just to see if you take the same inputs to compare how the performance is there? Because I would expect that if you really have the same inputs, the performance should be rather similar. And in that way, maybe one can exclude if it's a matter of parameter settings or not, or if it really pertains to the data. That would also be one idea, maybe to single out where the problem could be. Yeah.
Oh, thank you. Thank you for your suggestion. I have not yet tried it out. Yes, it's. I think it's worth trying. Thank you very much. I'll do it.
Okay, so the next question is from the Lasagna.
Okay, thank you very much for your presentation. My question is whether you have considered to think of every token not just as a string, but as a set of different features. For example, as pointed out now, for example, to bring the lemma, even the written form, the transliteration, the morphological annotation in, so that to not to have only one feature for the for every token, but to see every token even as a vector and to compare again vectors with each other. So it is for sure much more complicated, but for pattern recognition might be interesting. Even the syntactical forms, for example, how the syntactical forms are repeated in different texts just for the typology of the text, whether you have tested such ideas or not.
I have not tested it using the syntactic features, but it's a very good point. Just last year and this year too, I just focused on the semantic features, the semantic levels, and I so to say, ignore the syntactic features. So it's a good starting point to include the syntactic features, and it's more better. It's even better to compare syntactic features and what I get from the analysis of semantic features. It's thank you. It's a good point.
Okay, so I think it's almost time. So thank you, Kyogoku-san. It's nice talk.
Right.